Okay, so real quickly I want to go over some key things about springs. A spring can either be oscillating horizontally like this, or you could have a spring oscillating vertically like that. Let's start with this vertical one here. So first term to know is the equilibrium position. So if you just have a mass that's hanging from a spring, it's not moving, it's just at rest. So pretend that this thing is just completely at rest. This point right here is referred to as the equilibrium position, right? Now why do we call it the equilibrium position? Because if this mass is just hanging here, right, so here's the mass, we got mg down, we got force of spring up, force of spring is up, and that's equal to kx, where x is how far the spring was stretched. Now look, if the mass is just hanging there at rest, what has to be true about these forces? They have to be equal. In fact, you know, sum the forces. You sum the forces, you get kx up, mg down. The sum of the forces equals ma. But if it's at rest, the acceleration is 0. So therefore, kx equals mg. Now look, this is one way you could find the spring constant. What must the spring constant be? mg over x, where x is how far the spring was stretched to get to that equilibrium position. Okay? Now, let's set this mass into motion. Let's set the mass into motion. So we pull the mass down. So you grab the mass, you pull it down like this, and you release it, right? So then what's the mass going to do? It's going to go doing, doing, doing. It's going to oscillate where the equilibrium position's at the middle. All right, so a term to know. So here we have the equilibrium. This is the equilibrium. Maximum distance from the equilibrium. Anybody know the name of that term? You've heard it before. Amplitude. The amplitude of the oscillation is the maximum distance from the equilibrium. So same thing over here. If it's a horizontal oscillation, you have the equilibrium position, and then this would be the amplitude. Like that. Okay? Hey man, in chemistry you did waves. You guys studied waves. Remember amplitude for waves? So here's a wave. What did you call the line? If you drew a line right down the center of the wave, if the wave died, that's where it would die to. What do we call that dotted line down the middle? That's the equilibrium position of the wave. So for a wave, look it's the same thing. It's the amplitude is the maximum distance from the equilibrium. So we got it, you know, it's the term for waves. For a pendulum, you have an amplitude. It's how big the swing is measured from the equilibrium position, which would be like the point where if the mass stopped swinging. Okay, so that's amplitude. Now, let's keep going here. Look, one thing we've been talking about is this. If there's no friction, so say like, let's look at this horizontal mass right here. Let's say that this guy is oscillating back and forth with no friction, which means he'd go forever. He'd go forever and ever and ever and ever until an outside force came and made him stop. Okay? What type of energy would this mass have when he's over here, when he's right here? Well, first off, let me ask you this. What's going to be the velocity over here at this end of the oscillation? For a split second, this mass is going to stop. The velocity here is 0. And then what's the velocity over here at the other end? 0. Okay? So what's the only energy that it has right here? The only energy is going to be potential energy of spring, or you could call it potential energy elastic. Okay? Why no kinetic over here? Because it stopped. Okay, what type of energy does it have over here? Potential energy of spring again. What type of energy is it going to have in the middle right here? All kinetic. Now, guys, why no potential in the middle at the equilibrium? So this middle right here, the middle here is the equilibrium position. Why no potential there? Well, is the spring stretched? No. Is the spring compressed? No. So it's all kinetic. Now, dudes and dudettes, the thing to realize is if this is a frictionless situation, these three energies are going to be what? They're going to be equal. The mechanical energy stays the same. It just changes from one form to another. Does that make sense? Now look, what if we look at a point midway, like right here, in between the equilibrium and the amplitude? What if we look right there? What type of energy is it going to have there? It's going to be kinetic and potential. Why will it have kinetic right here? Because it'll be moving. Why does it have potential? Because the spring is stretched a little bit. But guess what? This total energy, this circle is equal to this circle. Everything I have circled is equal if there's no friction. Does this make sense? Okay, and then lastly, let's look over here. This is a little trickier. Vertical oscillations are a little trickier when you look at the energies. Okay, what type of energy is it going to have down here? Right here, it's going to be what? Oh, by the way, what's going to be the velocity down here? 0. What's going to be the velocity up here? 0. And where's the maximum velocity? The max velocity is going to be here. This is going to be max. Same thing over here. The max velocity is right there. Okay? So let's look at the energies. So what type of energy are we going to have down here for the mass oscillating vertically? It's going to be all potential of spring. 100% potential of spring. What type of energy are we going to have up here? It's going to be all potential of gravity. Why no spring energy? Because the spring, when the mass is all the way up top, is the spring stretched? No. Is it compressed? No. It's back to its starting point. It's not compressed or stretched. Okay? Oh, and by the way, whenever you talk of potential of gravity, you got to have a 0 point. I would have the 0 point down here at the lowest point. That would be the 0 point. Okay? And now what type of energy will the mass have at the middle? Does it have kinetic? Yeah. Does it have potential of gravity? Yeah. Does it have potential of spring? Yeah, because the spring is now stretched. So you'd have all three. That's a little that's pretty tricky. Okay. That's it.